What's up, guys? Welcome to Calculus Club. In this video, I will talk more about related rates. So this will be the second of two videos pertaining to the topic. All right, let's get into it. So in this video, I'm going to talk about substituting known relations. So if you've already seen my first video, you know that there was one more step in the steps to solving related rates that I didn't talk about yet, and that was substituting known relations, okay? So what do I mean by that? Well, imagine, for example, we have this cone, this inverted cone. Well, if we were to draw another cone inside of this cone, these two cones would be similar, which means like the ratio of the height to the radius. So for example, if the height is, let's say 10, and the radius is 3, then that ratio would hold true. And you need to know that in order to solve the problem, okay? This also will occur with like similar triangles, right? Like let's say we have this red triangle, and then you have this blue triangle that is drawn inside. So if you look at the sides, like you call this side X, you call this side Y, maybe you call this Z, and then you can call all of this. So Z is just like this little portion here. And then you call all of this, A, right? So you can set up, because you know that those must be similar triangles, you can set up a proportionality. You know the ratio of X to A equals the ratio of Y to this side, right? Well, what is this side? Well, that side would be A minus Z, okay? So with that information, you would be able to solve a related rate problem. Very common is a shadow problem where you have a person walking away from a light, okay? So if you can see that problem, you're gonna need to use this methodology. All right, let's do an example problem. So let's say you have an inverted conical tank. Water enters that tank at a rate of 2 meter cubed per hour. Okay, and I'll go ahead and just draw this. So this is the conical tank, right? An inverted cone. The tank has a height of 10. Okay, so let's just call this H and let's call this R. It has a height of 10 and a radius of 3. What rate is the water's height changing at the moment the radius is 1? Okay, so let's put together everything that this question tells us, all right? So first of all, we know water enters at a rate of 2 meter cubed per hour. So imagine that you have like a hose or something, right? But in general, water is going in, which means dV dt, the rate of change of volume with respect to time, is 2 meters cubed per hour, okay? The tank has a height of 10 meters and a radius of 3 meters. Okay, so that means at any time, all right, so if this water was full, we could clearly see that the ratio of H to R equals 10 to 3. Now, of course, as that water falls, each of these cones within that bigger cone would be similar. Okay, so this would always hold true. So H to R would always be 10 to 3. We'll rewrite that in just a second, but let's finish writing the rest of this information. At what rate is the water's height changing at the moment the radius is 1? So when R equals 1, so that'll be like here. So imagine that you have this little R equals 1. Okay, at that moment, what is dH dt? So dH dt is what we're looking for. The rate of change of height with respect to time. Okay, so the first thing you want to do is realize we're talking about volume of a cone. So what is the formula for volume of a cone? It's 1/3 times the area of this base times the height. The area of the base is, of course, pi r squared. So it's going to be 1/3 pi r squared times H. Now normally when we got a formula, we would differentiate with respect to time pretty quickly. When we're talking about these known relations, we're going to do some substitution first. Now the trick here is we're looking for dH dt, so we want to keep H in this equation, all right? So to keep h in the equation, we want to replace the r. So what we're going to do is rewrite this. So if we rewrite it, we would get h equals 10/3 r. But we want r in terms of h. So let's multiply both sides by 3/10. And we would get that r equals 3/10h. Okay? So now, in the same way that when we substituted in known constants, we were sure that if it's a constant, it never changes, okay? It always holds true. So the same thing is here. We can only substitute in a known relation if it always holds true. And regardless of the height of the water, it will always be true that the radius equals 3/10 h. So that means we can indeed plug this in, okay? So let's go ahead and plug this in. So now we're gonna get volume equals 1/3 pi times r, which we're gonna replace with 3/10 h squared times h. Now let's bring this all together, make it a little bit simpler. V equals 1/3 pi times, so you can just square everything. So 3/10 h times 3/10 h, which is going to be 9/100 h squared times h. So now we can combine a little bit. The 3 and the 9 are going to cross out. So we'll get volume equals to 3 pi over 100 times h cubed. Okay? And now that we have it in this form, we can differentiate with respect to time. Okay? And let me do it on the next page because I'm kind of running out of room here. All right, so this is where we were at. V equals 3 pi over 100 h cubed, right? Let me just double check, make sure that's right. So now we want to differentiate with respect to time, okay? So we're going to differentiate this with respect to time. And when we do that, we were going to get dv dt equals, well, 3 pi over 100 is just a constant, so we'll just write that. 3 pi over 100 times the derivative of h cubed is 3h squared, but then, of course, we need to differentiate implicitly. So 3h squared times dh dt. All right, so now we can insert some things so we can solve for our dh dt, okay? Well, what do we know here? We know dv dt is 2, so let's go ahead and plug in 2 for the dv dt equals 3 pi over 100 times 3h. So what is the h? Well, we're talking about the instant when r is 1, okay? So we can plug in here to solve for our h. So if r is 1, so 1 equals 3/10 h, and then of course we can multiply both sides by 10/3 to get that h alone. So that means h equals 10/3. So at the instant when r equals 1, that h is 10/3 for that, okay? All right, so we're gonna plug in 10/3, square it, times dh dt, that's what we're looking for. All right, so let's plug some things in here. It's gonna be kind of nice. Some things are gonna go away. When I square that 10/3, that's gonna be 100. Let me just, I'll just write this all out so we can see it. So 2, 3 pi, let me go ahead and bring that 3 and that 3 together. Okay, that's gonna make it 9 pi over 100 times 100 over 9 times dh dt. All right, you can see this is going to work out nicely. The 9s and the 100s cross out. So 2 equals pi dh dt. And of course, we can divide by pi. So at that instant, the rate of change of height with respect to time is going to be 2 over pi. And the units are meters per hour. Okay, so at that instant, the rate at which that height is increasing is 2 over pi meters per hour. Okay? So yeah, so that's how you do that one with a known relation. Now what I want to do is I want to show you how to solve the problem if you didn't have a known relation. Okay? So let's say that we go ahead and we just differentiate right away. Instead of making the substitution r equals 3 over 10h, and let me rewrite it here, r equals 3 over 10h, because we will need it in just a second. Okay, if we differentiate all of this with respect to time, so this of course is going to be dv dt. Pi over 3 is a constant. How about r squared times h? How would we differentiate that? Pause the video and think about that for a second. So I hope you pause the video and I hope you realize that what we need to do there is use the product rule, okay? So we need to look at each of these separately. We need to look at r squared and we need to look at h. And if you remember the product rule, you take the derivative of the first, leave the second alone, plus leave the first alone, the derivative of the second, right? So this would be dv dt equals pi over 3, that's a constant, times 2r dr dt times h, right? So this is the derivative of the first is 2r dr dt, h is the second, we leave it alone, plus leave the first alone, r squared, times dh dt. So you would get all of this long problem here, okay? And now you would need to plug in, remember we're still looking for dh dt, right? We're still looking for this here. So when we plug in, remember we were talking about when r equals 1, okay? We also need an h. What was h when r was 1? It was 10 over 3, okay? So that h equals 10 over 3. So we can plug some stuff in here. Let's see. So this is going to be pi over 3 times 2r, so 2 times 1. And now we need dr dt, okay? Well, dr dt isn't given to us, but we can find it by differentiating. Let me use a different color here so this stays a little bit clear. By differentiating that r equals 310h with respect to time. So if we differentiate that with respect to time, what we're going to get is dr dt equals 3 over 10 dh dt. Okay, so we can plug that in for dr dt. So we'll have a couple unknown dh dt's, right? So let me flip back to this blue color. So we're going to have 2 times 1 times dr dt, which we have just found to be 3 over 10 dh dt. Okay, times our h, which at that instant is 10 over 3. Okay, plus r squared, which is 1 squared, which is just 1, but I'll just write 1 squared. dh dt is again what we're looking for. All right, so let's combine all of this stuff and we're gonna get, let's just leave that pi over 3 here at the front. All right, we got these 3's will cross out and these 10's will cross out, so that's nice. So we'll get 2 dh dt plus 1 dh dt, which is just dh dt, okay? And then this is going to be pi over 3 times 3 dh dt, right? Because 2 dh dt's plus 1 more dh dt's would give us 3 dh dt's, okay? The 3's cross out. Oh, by the way, I forgot to plug in for dv dt. dv dt is 2, right? So let me go ahead and plug in dv dt. So 2 equals all of that. 2 equals all of that. 2 equals all of that. These 3's cross out. So then to get dh dt alone, I just divide by pi and I'm left with dh dt equals 2 over pi. And my units are meters per hour. So 2 over pi meters per hour, that's the same thing that I got. Oh, where'd it go? Yeah, sorry, I went back too far. Here. So you can see that was our final answer. When we substituted the known relation, we got that 2 over pi meters per hour. Same thing if you did it this long way. Just takes a bit longer, but again, you can do it in this way if you want. In the same way, you don't have to plug in for the constant. It just makes your life a little bit easier. Okay? So yeah, so now if you understand known relations, you should understand how to do any related rates problem. So let's go over all the steps. All right, what's the first thing we do? We draw the picture, okay? Draw the picture. Sometimes we draw one static and one dynamic, especially when we're dealing with 2 triangles, right? Second thing is we will determine a formula that relates the problem, the quantities in question. Third thing, which is actually optional, but we can minimize the number of variables by substituting constants or substituting known relations. And I might write optional here, okay, just so you remember that. But definitely, I would recommend doing it. It's gonna make your life much easier. And then once you've done that, you just differentiate with respect to time, and then you solve for the unknown value, okay? So that's all there is to it. Yeah, so I hope these videos, I hope you watched both of my videos and they made related rates much, much easier. Also, I just wanted to let you know that I have created a full-length calculus course. So if you're interested in learning calculus in the easiest, most intuitive way that I can possibly think of to teach a student, then definitely check out the information. I've put the link below where you can take a look. So yeah, so thanks a lot for watching, and I hope you tune in for the next video. All right, bye-bye.